In the older imagination, a robot is a precise creature of repetition, a body of metal and actuators that moves through the same narrow corridor of motions. As long as the corridor is kept clean, the lighting stays steady, and the world does not surprise it. But the quieter revolution now unfolding in laboratories, fabrication shops, and construction sites begins when we stop treating the machine as a strict executor of a finished blueprint and start allowing it to take part in the blueprint's becoming. So that design and build blur into a continuous loop of sensing, proposing, testing, correcting, and learning. A loop that looks less like a factory line and more like a patient craft tradition where the hand adjusts pressure by feel and the mind revises the plan mid-stroke. Before we move on, a quick subscribe helps this stay in your feed whenever you're ready to relax and learn again. In this newer loop, the essential shift is not simply that the robot can move in more directions, or that its motors are stronger, or that its grippers are gentler. It is that its internal model of the world can be updated by experience. And that update can change what it decides to make next, which is why so many of the most interesting systems in advanced robotics are paired with software that searches enormous spaces of possibilities, then returns to the physical world to discover which possibilities actually survive contact with gravity, friction, temperature, and imperfect materials. When that cycle is calm and persistent, a machine can begin to learn the stubborn truths that builders have always known in their bones, that a beam is never perfectly straight, that a joint's strength depends on the tiny accidents of contact, that a wet day changes how surfaces receive adhesive, that a gust of wind shifts a suspended panel by a few millimeters that matter, and once those truths can be sensed and folded into the next decision, we step beyond programmed robots and into intelligent crafters that behave like adaptive apprentices. Not because they have become human, but because they have become responsive in a way that rigid automation cannot be. You can see the early shape of this future in the modest but telling places where fabrication already meets local context. Like digital fabrication workflows that let a neighborhood workshop produce a customized medical brace or a replacement part on demand rather than waiting for centralized manufacturing. A shift that is not only about convenience but about a deep change in what counts as standard, because when the cost of variation drops, the world can be built more like a landscape than like a catalog. With objects tuned to bodies, climates, and repairs, and with production that can happen nearer to the moment of need. A theme that has been articulated for years in the culture of fabrication laboratories, where tools are shared and designs travel as files rather than shipments, compressing distance into data and turning making into something that can be both local and global at once. In architecture, the same pattern begins to appear when design software does not merely draft a building, but continuously evaluates it against constraints and goals, daylight, structural stress, material usage, ventilation pathways, and then proposes geometries that no single designer would patiently enumerate by hand. And even when humans remain the final editors, the exploration itself changes the creative landscape by revealing strange but workable forms, trusses that branch like bone, lattices that place material only where forces ask for it, and joints that look implausible until analysis shows their efficiency. And once a design like that exists, robotic fabrication systems can give it a body with fewer simplifications. Because machines that print, mill, place, or assemble can follow complex tool paths without the fatigue that makes complexity expensive for human hands. Yet the most profound step happens when the built artifact is not the end of intelligence but a participant in it. When structures are embedded with sensing and feedback so that the physical environment becomes part of the design conversation. And the building is not a static answer but an ongoing question asked in concrete, timber, polymer, and steel. Because a structure that knows how it is loaded, how it is swelling with moisture, how heat is moving through it, or how microcracks are evolving can be maintained and even subtly reshaped in response to its own condition. That idea can feel futuristic, but the logic is already visible in research on robotic construction that borrows from social insects, where a team does not carry an entire cathedral in its head, but instead follows local cues, incremental rules, and shared signals to produce coherent structures without a central foreman micromanaging every placement. And what makes this line of work quietly unsettling is the way it reframes construction from a top-down act of command into a bottom-up act of emergence, where the final form is not fully specified in advance, but arises from repeated interactions between agents and materials. In such systems, self-assembling does not have to mean a science fiction instant unfolding. It can mean a patient choreography in which components, robots, and partial structures guide one another, like a shoreline that slowly shapes drifting wood into patterns of accumulation. Except here the shoreline is encoded in sensors, markers, and algorithms, and the driftwood responds with wheels, arms, and limited but reliable decision-making. The nearer-term versions of this are already practical in constrained domains: modular assembly in factories, autonomous placement of rebar ties, robotic bricklaying, large-scale additive construction, where a printer deposits material layer by layer. And the deeper promise is that when autonomy increases, the site itself becomes less brittle, because a machine that can perceive deviations and adapt can keep working through small uncertainties that would force a rigid process to stop and call for human rework. Even personalization, which sounds like a consumer luxury, becomes structurally important in this context, because the same ability to adapt and learn that allows a robot to adjust to a warped panel also allows it to adjust to a person's particular anatomy, movement, or medical needs. And once customization is routine, we begin to imagine cities that treat citizens less like identical units and more like diverse organisms sharing a common habitat, where ramps, grips, fixtures, acoustic treatments, and even room layouts might be iterated and tuned as demographics shift and as bodies age. Not through massive renovation cycles, but through ongoing small acts of remaking. The more you sit with that, the more adaptive architecture stops sounding like a marketing phrase and starts to resemble ecology. Because the built environment has always been a slow negotiation with weather and time, with foundations settling, with sun angles changing across seasons, with insulation aging and materials creeping under load. And what intelligent crafters offer is a way to keep negotiating after the ribbon cutting, by giving buildings an internal awareness that can trigger maintenance before failure, adjust shading before heat stress accumulates, or reroute airflow before mold finds a foothold. And by giving fabrication systems the ability to return and intervene with minimal disruption, like a careful gardener pruning rather than a demolition crew resetting the entire garden. In that future, a building that grows does not have to sprout walls overnight. It can grow in the quieter sense that it accrues capability and fit, adding a structural rib where usage patterns reveal unexpected stress, thickening an exterior layer where storms have intensified, reconfiguring interior partitions as families change. And doing so through a partnership of algorithms, sensors, and robotic tools that treat the building as a living project rather than a finished object. This also changes how we think about the boundary between design and maintenance. Because maintenance becomes a form of continuous design guided by data, and design becomes a form of anticipated maintenance that plans for parts to be replaced, surfaces to be resurfaced, and modules to be upgraded. And the intelligence that enables this is not some single, all-knowing mind, but a fabric of narrower intelligences, each trained on specific tasks, each grounded by physical feedback, and each made safer and more reliable by the humility of measurement. There is underneath the calm of these possibilities a tension that comes from scale, because when the same adaptive systems that can personalize a small object are applied to infrastructure, the stakes rise from comfort to continuity, from aesthetics to safety. And the learning loop that makes a robot capable also makes it unpredictable unless its objectives are bounded and its actions are constrained. Yet if we imagine careful guardrails, verification, monitoring, conservative behavior in uncertain conditions, then the picture that emerges is not of runaway machines, but of an expanded craft. Where computation explores, robots execute, sensors testify, and humans set the values and the thresholds that define what good means. It is in that expanded craft that the future can be visualized most clearly. Not as a skyline of alien forms, but as neighborhoods that feel quietly more attentive, where the physical world is less wasteful because it is less overbuilt, less fragile because it is less blind, and more humane because it can respond, slowly and continuously, to the people and the climates that pass through it. And the first step toward that world is simply accepting that making is no longer a one-time act, but a conversation that can continue as long as the structure stands. If the first quiet change is that machines can keep a conversation going between plan and reality, the second is that the plan itself begins to feel less like a drawing and more like an evolving organism. Because in generative design, the shape is not chosen from a shelf of familiar forms, but discovered by searching through vast families of possibilities under constraints that resemble the world's own insistence. The insistence of loads and safety factors, of stiffness and vibration, of sunlight and glare, of acoustics and airflow, of embodied carbon and cost. And when that search is done by algorithms that can iterate tens of thousands of candidates, each evaluated by simulation and filtered by requirements, the result is often a geometry that looks uncannily natural. Before we move on, if you like learning this way, you can quietly hit subscribe so you don't lose this channel later. Not because it copies nature in a decorative way, but because it shares nature's economy, placing material where it carries stress and removing it where it does little, as if the design had been patiently worn into efficiency by time. One of the older foundational ways to formalize that patience is topology optimization, where the designer sets the domain, the loads, and the constraints, and the algorithm gradually erodes material from regions that contribute least to structural performance, repeatedly solving and updating until a sparse, force-following skeleton emerges. And this matters not only because the resulting forms can be lighter and stronger, but because the process shifts the designer's role from drafting a single answer to curating a problem statement, deciding which objectives deserve priority and which trade-offs are acceptable. A role that is quietly ethical as well as technical, since an algorithm that optimizes for minimum mass without caring about manufacturability can produce a phantom, and one that optimizes only for cost can produce something brittle in other senses, like a street that traps heat or a room that starves daylight. In practice, designers fold additional layers into the search: fabrication constraints, minimum feature sizes, preferred member angles, available stock dimensions, so the machine's imagination stays tethered to what can actually be made. And the tether becomes even more important as we move from components to buildings, where the tolerant stack-up of thousands of joints, the variability of materials, and the unpredictability of weather can make a perfect simulation feel like a mirage, unless it is constantly corrected by measurement. This is where advanced AI methods begin to show their quieter strength, not as mystical creativity, but as pattern finding across messy data. Because modern systems can learn surrogate models that approximate expensive simulations, can propose designs that satisfy constraints more quickly, and can use reinforcement learning or other decision frameworks to navigate trade-offs while respecting hard safety boundaries. And yet the most meaningful capability is often simply the capacity to update beliefs when the world disagrees. To treat a simulation not as a verdict, but as a hypothesis that must be tested against strain gauges, laser scans, thermal cameras, and the small, stubborn evidence of parts that do not quite fit. When you watch this process closely, you start to see design not as a moment, but as a trajectory. And the form of a structure becomes the trace of countless micro-decisions, each informed by a little more knowledge than the last. Which is why the evolution of form in AI-guided design can feel both unfamiliar and strangely inevitable, as if the shape had been waiting inside the constraints all along. What lets these shapes step out of software and into the world without being sanded down into conventionality is the parallel evolution of robotic fabrication, because digital complexity is cheap on a screen but historically expensive in labor. And the construction industry has long relied on repetition, not because repetition is beautiful, but because repetition is reliable and financeable. Yet robotic systems can make variation less punishing by executing intricate toolpaths and precise placements with steady attention. Whether the tool is an extruder laying down a bead of material, a milling head carving foam molds, a robotic arm placing bricks or tying reinforcement, or a gantry-scale printer tracing walls in layers. Large-scale additive construction in particular has become a kind of slow-moving demonstration of what happens when you remove the need for formwork in some contexts and replace it with controlled deposition. Because formwork has always been one of the hidden governors of architectural freedom, a temporary structure whose cost and labor quietly dictate the permanent structure's geometry. And when a machine can print a curve as easily as a straight line, some constraints soften, though others immediately harden, like the physics of curing, the risk of voids, the sensitivity to temperature and humidity, and the complicated question of how printed materials bond across time. Especially when layers are interrupted by the real rhythms of a site. Contour crafting and related approaches have framed this possibility for decades, proposing automated, layer-based construction that can reduce labor and increase speed. But the deeper story is not speed, it is feedback, because the most capable fabrication robots do not only follow a path, they observe the path they have made. Scanning for sag, measuring bead width, adjusting flow rate, and compensating for drift. And that ability to close the loop is what turns a brittle automation into an adaptable craft, especially in construction where the workpiece is too large to be kept in a controlled chamber. Alongside printing, robotic assembly has been quietly advancing in ways that matter for the built environment, from automated placement of prefabricated modules to on-site manipulation of heavy components with collaborative safety systems. And what makes assembly robotics distinctive is that it forces intelligence into contact, into the intimate uncertainties of alignment, friction, torque, and compliance, where a small misreading can jam a joint or damage a part. And so these systems increasingly combine precise sensing, vision, force-torque feedback, LiDAR, tactile arrays, with control strategies that allow a kind of careful yielding. A willingness to feel around within safe bounds until the parts agree, which is exactly the kind of embodied negotiation that human builders perform constantly without naming it. As fabrication becomes more capable, it also begins to reshape design upstream. Because once designers know that a robot can reliably place unique parts, they can shift from designing around standard beams to designing families of members whose dimensions vary continuously. Each one cut or printed to its exact role. And that is where generative design and robotic fabrication begin to reinforce each other, one proposing complex, force-following architectures, the other making those architectures physically plausible without translating them into a blunter language. Yet there is a third thread, more subtle and perhaps more transformative, which is the emergence of material intelligence. The idea that some of the behavior we want from structures can be delegated not only to sensors and motors, but to matter itself. To materials that change properties with temperature, humidity, electric fields, light, or chemical conditions. And to composites whose internal geometry encodes responses in the way a pine cone encodes the opening and closing of its scales. When robots work with such materials, fabrication becomes less like assembling inert blocks and more like setting conditions for later transformation. Because you are not just placing a beam, you are programming a response. Deciding how a laminate will bend as it absorbs moisture, how a shape memory polymer might recover a form when warmed, how a cementitious mix might heal microcracks through chemical processes, or how an active facade element might curl to shade a window as the sun shifts. The term 4D printing was introduced to describe structures that change shape over time after being printed. And while the phrase can sound theatrical, the underlying concept is sober, that time can be treated as an axis of design. and that the final, in-service geometry might be different from the geometry that comes off the printer bed, which in turn invites a new kind of collaboration between algorithm and fabrication robot. Because the robot must place material with an awareness of anisotropy, of fiber directions, of curing gradients, of residual stress, and of the future environment in which the object will live. Imagine a robot printing a composite panel whose internal pattern causes it to flex slightly as humidity rises, tightening seals during storms and relaxing them during dry heat. Or a robotic system laying conductive traces into a surface so that the surface can sense strain and warmth. Or a construction arm embedding sensor networks as casually as rebar, turning the structure into a measured object rather than a mute one. And notice how the intelligence here is shared, partly in software, partly in the robot's control, and partly in the material's own physics, which can be reliable in a way that complex actuators sometimes are not. This distribution of intelligence matters because it offers a path to robustness, since a building that relies on thousands of moving parts to adapt may be fragile. But a building that adapts through passive material responses, guided by limited, well-verified actuation where necessary, can remain calm and dependable. And when we combine that with AI-driven design that explicitly accounts for uncertainty, fatigue, and environmental variation, we begin to see a different kind of architectural future. One where form is not frozen at completion, but continues to negotiate with the world through subtle shifts. And where the role of robotics is not to replace builders with cold precision, but to extend what builders can responsibly attempt. Enabling structures that are lighter, less wasteful, more expressive of forces, and more capable of adjusting to the changing conditions of climate and use. The deepest impression, when you let these threads settle together, is that the architect of tomorrow may be less a solitary author of static forms and more a careful composer of systems. Defining constraints, selecting materials that behave, and overseeing robotic fabrication that listens, so that what we build can remain quietly aligned with reality long after the first day it opens. As design and fabrication grow more adaptive, the next threshold is not a grand leap in strength or speed, but a refinement of touch. Because a world built by intelligent machines will only feel trustworthy if those machines can interact with the ordinary delicacy of daily life. With objects that bruise and crumple, with surfaces that scratch, with joints that bind if approached at the wrong angle, and with human bodies that cannot be treated as obstacles or afterthoughts. And this is why so much of advanced robotics now concentrates on sensing and contact, on the subtle physics that lies between a gripper and a tool handle, between a robotic foot and shifting rubble, between a manipulator and a cracked pipe that must be turned without snapping. Haptic feedback, once a specialized term, is essentially the recovery of something that people take for granted. The ability to feel forces and textures, and to use those sensations to guide motion. And in robotics, that guidance can come from force torque sensors at the wrist, from tactile arrays on fingertips that detect pressure distributions, from vision systems that infer slip before it becomes a drop, and from control algorithms that treat contact not as a failure mode, but as a primary signal. Allowing the robot to comply rather than fight, to yield slightly when the world pushes back, which is the difference between an arm that jams a part into place and an arm that searches, aligns, and seats it gently. In the calmness of such control, there is a kind of respect for materials, because the world is not a set of ideal rigid bodies, but a collection of deformable, imperfect things. And the moment a robot can measure that imperfection in real time, it can behave less like a blunt instrument and more like a careful craftsperson. Tightening until the gasket compresses just so, lifting a pane of glass while sensing its flex, guiding a cable through a crowded cavity while feeling when it catches. And those small competencies accumulate into a broader capability that matters for construction and infrastructure, where tasks are rarely neat, and where the most expensive errors are the ones made at interfaces, at edges, at seams where systems meet and tolerances stack. This sensitivity also changes how robots can work with people, because collaborative robotics is not only about adding safety cages and emergency stops. It is about making motion legible, making behavior predictable, and making the sharing of space feel natural enough that a human worker can focus on judgment rather than vigilance. Modern collaborative robots often limit force and speed by design, use torque sensing to detect unexpected contact, and plan trajectories that avoid startling sweeps. But the deeper challenge is coordination. The quiet choreography of handing over a tool, holding a component steady while a person fastens it, or adjusting the pose of a heavy panel in response to a worker's cues. And this is where AI begins to participate not as an abstract brain, but as a translator between intention and action. Using vision to track gestures, using models of human motion to anticipate where a partner will step, and using task representations that allow flexible turn-taking rather than rigid scripts. In a construction setting where a site changes day by day, that flexibility is essential because scaffolds appear and vanish, materials arrive in irregular lots, and weather reshapes schedules. And so the most useful robotic teammate is one that can perceive the evolving scene, understand the constraints of the moment, and contribute under supervision, without demanding that the entire site be rebuilt into a pristine factory. This does not mean the human disappears. It means the human role shifts toward planning, oversight, and quality judgment, while machines handle the repetitive lifting, precise placement, and exposure to hazards. And if the collaboration is done well, it can reduce injury and fatigue in a field that has long been physically punishing, though the benefits depend on careful implementation, training, and a culture that treats safety as a system property rather than a slogan. The same blend of sensing and autonomy becomes even more consequential in disaster response and repair, where the environment is hostile to certainty, where maps are outdated minutes after a collapse, and where the most urgent work must often be done in spaces too dangerous for sustained human presence. Here, the promise of autonomous systems is not to replace rescuers, but to extend them. To send machines into voids that may shift, to inspect bridges after earthquakes, to survey flooded substations, to locate leaks, gas pockets, or hotspots, and to do it quickly enough that human teams can decide where to risk themselves and where to wait. Research and real deployments in this domain have shown how varied the robotic body must be to meet varied terrain. From tracked platforms that crawl over debris to legged robots that can step across gaps, from aerial drones that map from above to snake-like robots that slip through narrow conduits. And the common requirement is perception under stress. The ability to build a usable model of a scene from partial, noisy data, sometimes without GPS, sometimes through smoke, dust, or darkness. And then to act within that model conservatively, because in disaster zones, the cost of a wrong move is not a failed task, but a destabilized structure or a blocked passage. The practical intelligence here often looks less like bold exploration and more like restraint. Like a machine that pauses when it cannot verify footing, that backs away when force readings suggest a wall is load-bearing, that chooses a slower path because it keeps vibration low. And this is where the calm aesthetics of careful robotics begins to align with the ethics of response, because the best disaster robot is not the most dramatic, but the most dependable. The one that can be trusted to gather information, to place a sensor, to deliver a small payload, to cut power safely, or to shore a weak element without improvising beyond its certification. In infrastructure repair, autonomy can take on an even quieter role. The steady maintenance work that prevents disasters from becoming headlines, and there's a growing recognition that much of our built world fails not in spectacular ways, but in slow, distributed deterioration through corrosion, fatigue, water intrusion, and thermal cycling. And that the scale of bridges, pipelines, seawalls, rail systems, and power networks makes human-only inspection both costly and incomplete. Robots equipped with cameras, ultrasonic probes, LiDAR, ground-penetrating radar, or chemical sensors can patrol and scan. And when paired with machine learning models trained to detect cracks, spalling, misalignment, or unusual heat signatures, they can flag anomalies earlier, turning maintenance into something closer to medicine, where screening and early intervention prevent acute crises. And in some cases, robotic systems can also perform small repairs, applying sealant, cleaning and recoating, tightening fasteners, or replacing modular components. Tasks that are not glamorous but are exactly what keeps a city functional. There is a delicate line here, because automation in public infrastructure must be validated to a higher standard than automation in a private workshop. And so autonomy tends to arrive first as decision support and supervised operation, then gradually expands as reliability is proven. Often in constrained environments like tunnels, offshore platforms, or industrial plants, where repeated routes and controlled access make verification more tractable. If you look across these domains, touch, collaboration, disaster work, maintenance, you can feel a shared theme. That the sentient sculptor is not a robot that daydreams, but a robot that senses, a machine that earns its agency through careful measurement and controlled action. And this is why advances in perception and learning are inseparable from advances in hardware. From better tactile skins and more robust joints, from compliant actuators that can absorb shocks, from power systems that last long enough to be useful, and from communication links that remain secure and reliable when the environment is chaotic. The future that emerges from this is not one in which robots roam freely, indifferent to human presence, but one in which they are embedded into the practical rhythms of building and repair, arriving where risk is high and attention is scarce, offering strength with gentleness, precision with feedback, and autonomy bounded by a constant dialogue with human oversight. And if that dialogue remains central, the built world can begin to feel less like a set of frozen artifacts and more like a maintained, responsive habitat that is cared for with a steadiness that human hands alone, stretched thin by scale, have never been able to provide. There's a point, subtle at first, when creation stops being a one-way act and begins to fold back on itself, when the thing that is made becomes a source of information that can change how it will be made again. In advanced AI robotics, this is the moment where fabrication, inspection, maintenance, and improvement start to merge into a single continuous practice, so that the boundary between building and caring for what was built becomes less like a handoff and more like a living circulation. In the older pattern, we design, we construct, we inspect, we repair, and each phase is separated by paperwork, by delayed discovery, by the assumption that the object will behave roughly as expected until it visibly fails. But in the emerging pattern, the object is instrumented, observed, and interpreted from the beginning. And the tools that made it may return to it with the same familiarity a gardener has with a long-tended tree, not to replace the whole form, but to correct, reinforce, or refine the parts that time has stressed. Structural health monitoring gives this shift its technical backbone. If a bridge or building can be measured continuously, through strain gauges, accelerometers, acoustic emission, fiber optic sensing, corrosion probes, temperature and humidity arrays, then deterioration does not remain a rumor inferred from occasional inspections. It becomes a trackable signal, and once a signal exists, algorithms can learn baselines, detect anomalies, and estimate remaining useful life, not as prophecy but as probabilistic judgment grounded in data, which in turn enables maintenance to move from reactive to predictive, from emergency closures to scheduled interventions that can be smaller, cheaper, and safer. When robots are introduced into this loop, the monitoring does not only point to trouble. It can also trigger action, dispatching crawling or flying inspection platforms to verify a suspected crack, sending a manipulator to clean and reseal a joint before water ingress spreads, or coordinating a temporary support placement while human engineers review the situation. And the deeper promise is not simply that machines will do more maintenance. It is that maintenance will become more precise, more local, and more frequent. Like the difference between waiting for a toothache and brushing every day. This self-correction becomes even more compelling when the materials themselves participate, because a structure that can heal small damage reduces the need for intervention and slows the march from micro-crack to failure. And self-healing concretes, for example, have explored multiple mechanisms, capsules that release healing agents when cracks form, bacteria-based systems that precipitate minerals, admixtures that promote autogenous healing, each with its own limits and trade-offs. Yet the underlying idea is steady and realistic, that a great deal of structural degradation begins at scales too small to justify immediate human repair, and if those scales can be managed automatically, the entire life cycle changes. Robotics can complement these materials by placing them selectively where microcracking is most likely, by embedding capsule networks or vascular-like channels during fabrication, or by revisiting vulnerable zones to apply targeted treatments guided by sensor evidence. And what begins to emerge is a maintenance ecology in which some repair is chemical and internal, some is robotic and external, and some remains human and supervisory, chosen not by tradition, but by what is safest and most effective in each context. In this ecology, even the notion of inspection changes, because inspection can be embedded into the act of building itself. With robots that scan each layer of an additively manufactured wall for voids, measure curing temperatures, verify reinforcement placement, and record as-built geometry, producing a detailed provenance of the structure that can later be compared against new scans, making drift and deformation visible long before they become visible to the eye. The phrase digital twin often enters here, sometimes used loosely, but at its most grounded it names a practical continuity between a physical asset and a computational model that is updated by real measurements. And that continuity matters because many maintenance decisions are not simply about detecting damage, but about understanding consequences. Whether a crack is cosmetic or structural, whether a temperature gradient is normal or a sign of insulation failure, whether a vibration signature indicates an emerging fatigue problem. And a twin can serve as a place where these questions are tested, where sensor streams are fused with simulations and historical data to produce a living estimate of condition. If that estimate is trustworthy, it becomes a calm kind of foresight, allowing a city to prioritize repairs, schedule downtime, and allocate budgets with a clearer view of risk. But its trustworthiness depends on constant humility, on acknowledging uncertainties, validating models, and keeping human engineers in the loop for decisions that carry public safety implications. Because a twin that drifts into false confidence can be more dangerous than no twin at all. When robots are part of the twin's feedback loop, the twin stops being only a dashboard and becomes a controller of interventions. Not necessarily issuing autonomous commands without oversight, but coordinating routines, inspection routes, sensor calibrations, minor remedial actions in a way that reduces the friction of care. And this is one of the quiet ways that autonomy can make infrastructure feel more alive, not because it thinks, but because it is tended continuously, like a ship with an attentive crew, rather than a derelict patched only after storms. The most psychologically significant shift, though, may be that the machines themselves begin to learn from the act of building, not merely from abstract datasets, but from their own embodied histories. From the record of where prints sagged on humid mornings, where fasteners cross-threaded when torque was too high, where a particular adhesive cured too slowly in cold shade, where a gripper slipped on a dusty surface, where a joint seated cleanly when approach angles changed by a few degrees. And this learning can occur at multiple levels, from simple parameter tuning to more sophisticated policy improvement. But the common direction is toward systems that reduce their own error over time, becoming more consistent and less wasteful with experience. In robotic fabrication, that can mean closing the loop between sensing and deposition so that material flow adapts to real bead geometry. Or using vision and force feedback to refine insertion behaviors in complex assemblies. Or employing optimization methods to update tool paths and support strategies to reduce residual stress. And while self-improving AI can sound like a dramatic claim, in practice it often looks like a careful accumulation of small refinements, an approach that is both more plausible and more valuable than grand leaps. Because in construction and infrastructure, the cost of small errors repeats at scale, and a modest improvement in consistency can translate into substantial reductions in rework, downtime, and embodied carbon. Yet learning in the physical world carries a particular kind of risk, and a system that learns by trial and error cannot be allowed to experiment freely where a mistake could injure people or compromise a load-bearing element. And so the most responsible forms of self-improvement are constrained by safety envelopes, supervised evaluation, simulation to reality pipelines, and staged deployment, where new behaviors are tested in digital environments, then in controlled mock-ups, then in low-stakes field settings, and only then in critical contexts, a progression that mirrors how aircraft software is validated. And that is one reason digital twins and high-fidelity simulation matter beyond planning, because they provide a sandbox where learning can occur with less danger. Even so, simulation is never the whole world, and so learning must be paired with conservative controls, formal verification where feasible, and monitoring systems that can detect when behavior drifts outside expected bounds. And in this sense, the most mature self-improving systems will not be those that chase novelty, but those that treat novelty as something to be quarantined and audited before it touches the public realm. When these elements, continuous monitoring, targeted robotic intervention, smart or self-healing materials, and constrained learning, are allowed to settle together, the concept of living infrastructure stops being metaphor alone and becomes a design paradigm. One in which the built environment is conceived as a long-term adaptive system rather than a static artifact, and where adaptation can be gradual, distributed, and mostly invisible, like homeostasis in biology, which does not announce itself with spectacle but with stability. A roadway that senses rutting and schedules micro-resurfacing before hydroplaning risk rises. A seawall that adjusts modular armor units as wave climates shift. A building envelope that notices persistent moisture and triggers localized drying and remediation. A transit bridge that tracks fatigue accumulation and changes its maintenance rhythm as loads evolve. These are not fantasies so much as extensions of existing engineering practices, made more continuous by sensing and made more actionable by robotics. And the calm tension lies in the fact that as soon as a system can correct itself, it can also, if mismanaged, correct itself in the wrong direction. Reinforcing a bad assumption, masking a deeper fault, optimizing for a metric that no longer matches human values, which is why self-correction must never be treated as a substitute for governance, but as a tool that amplifies whatever governance exists. In the end, the most profound blurring is not between machine and organism, but between building and stewardship. Because a world of AI robotics that can return to its own creations, measure them, learn from them, and repair them, is a world where permanence is no longer purchased by overbuilding and forgetting, but by attentive iteration. And if we choose to build that attentiveness into our structures from the start, through accessible components, embedded sensing, transparent data practices, and repair-friendly materials, then the future can feel less like a gamble on perfect construction, and more like an agreement to care continuously for the physical systems we depend on, with patience, verification, and a steady respect for uncertainty. When tools become intelligent enough to propose forms, to fabricate them with responsive precision, and to return later as caretakers that inspect and mend, the ethical questions do not arrive as an afterthought or a philosophical garnish. They arrive as engineering constraints in their own right, because the world that these systems sculpt is not only made of beams and panels and polymers, but of livelihoods, power, trust, and the quiet right to move through public space without being measured into someone else's advantage. The first tension most people feel, even if they do not phrase it technically, is the tension between displacement and creation. Automation has always carried a double truth, that it can remove dangerous, exhausting work and also remove the bargaining power of those who once did that work. In construction and manufacturing, the story is especially complicated, since a large share of cost and schedule risk lies in human coordination, site variability, and the skilled improvisation that keeps projects from stalling. So the arrival of capable robots can concentrate value in the firms that own fleets, data pipelines, and software, while hollowing out smaller subcontractors and reducing the number of stable entry points into middle-class livelihoods. Yet it can also create new roles that are not merely robot maintenance in a narrow sense, but roles in digital layout, sensor installation, quality verification, safety supervision, materials logistics, remote operation, and the craft of translating between intent and machine action. The ethical difference between these two futures often hinges on whether the transition is managed as a public project with training, standards, and shared benefits, or as a private race where labor becomes a disposable variable and the promised gains are captured narrowly. Even the most optimistic scenario requires honesty about timing and mismatch, because jobs can disappear quickly while new roles appear slowly and demand different skills. A society that wants the benefits of intelligent fabrication without the social brittleness must treat reskilling as infrastructure, not as an individual moral obligation. That means funding apprenticeships, supporting community colleges and technical institutes, and creating portable credentials that let a worker move from one employer's proprietary ecosystem to another without starting over. Otherwise, efficiency becomes a word that quietly means that risk is pushed downhill. The second ethical canvas is control and autonomy, and here the calm danger is that systems can become capable enough to act at scales and speeds that make human oversight feel ceremonial, especially when margins are thin and incentives reward throughput. In robotics and AI safety, a helpful way to think about this is that autonomy is not a single switch, but a ladder of delegated authority. The rung you choose must match the stakes of the decision. Letting a robot adjust a toolpath to compensate for a measured deviation is ethically different from letting it decide that a load-bearing element is good enough when the sensor data is ambiguous. Both are different again from letting a system reconfigure a public-facing space in ways that affect accessibility, crowd flow, or emergency egress. The temptation, especially for organizations under pressure, is to move oversight from active supervision to passive auditing. Then to delay audits because everything seems to be working, and then to discover too late that working meant that the system found a stable pattern that satisfied a metric while violating a value. Like a scheduling algorithm that optimizes cost by consistently assigning the noisiest construction windows to the same vulnerable neighborhood. Or a maintenance prioritization model that learns to favor high-visibility districts because historical data encodes political attention. These are not far-fetched failures of imagination, they are ordinary failures of governance. The antidote is not to reject autonomy but to specify it, to define decision boundaries, to require explainable traces for safety-critical actions, to implement conservative fallbacks, and to keep humans meaningfully in the loop where judgment is inseparable from public accountability. That means clear lines of responsibility that cannot be dissolved into the fog of the system decided. A third ethical surface appears once we accept that adaptive buildings and robotic fabrication will rely on sensing, because sensing is what makes adaptation safe. And yet sensing can easily become surveillance when it is not bounded. A building that knows its own strained state may need only structural sensors, but a building that personalizes itself can drift toward tracking occupants, inferring routines, and optimizing comfort in ways that may feel benign. Until the same data is repurposed for policing, insurance pricing, employment decisions, or the quiet sorting of who is welcome. And because the built environment is inescapable, the ethical stakes are higher than in consumer gadgets, since opting out can mean opting out of public life. Responsible design therefore needs data minimization as a first principle, collecting only what is necessary for safety and function, processing locally when possible, and discarding raw data quickly. It also needs strong limits on secondary use, and it needs transparency that is not merely a sign on the wall but a comprehensible contract with occupants about what is measured, why it is measured, who can access it, and how long it persists. Without such commitments, living infrastructure can become a polite mask for an environment that watches. The most unsettling kind of control is the kind that feels like convenience. Alongside privacy sits security, because once robotics and AI are embedded into construction and maintenance, cyber risk becomes physical risk. The vulnerabilities are no longer limited to data breaches but extend to sabotage, ransom, and cascading failure, whether through compromised firmware in a sensor network that feeds false readings into a maintenance system, or through an attack on a fleet management platform that controls autonomous inspection drones, or through subtle corruption of design files that causes a printer to lay down insufficient material in a critical zone. What makes this risk distinctive is that it exploits the very connectivity that gives the system its power. The ethical response here is partly technical: secure boot, signed updates, network segmentation, intrusion detection, redundancy, and rigorous testing, and partly institutional, demanding procurement standards, supply chain audits, and incident response plans that assume compromise is possible. because in a world where infrastructure is increasingly automated, resilience cannot be an optional feature or a public relations line. It must be a baseline requirement that is verified repeatedly, much like structural safety factors are verified in traditional engineering. Then there is the question of bias and inequity, which can feel abstract until you notice how design and optimization inherit the values of their inputs, and how historical data can encode historical neglect. If an AI system learns from past maintenance records, it learns not only where things broke, but where people looked. And if inspections were sparse in poorer areas, the data will be sparse there too, leading the system to underestimate risk precisely where the unknowns are largest. If a generative design tool optimizes for cost under a developer's constraints, it may consistently produce smaller windows, poorer ventilation margins, and lower quality materials in housing intended for those with less political power, while producing healthier, more resilient buildings elsewhere. The machine will do so with a calm confidence that can make inequity harder to argue against because it appears objective. Addressing this requires more than diverse data sets. It requires explicit fairness objectives, mandated safety and health minima that cannot be optimized away, and public oversight structures that treat the built environment as a shared good, not merely a market product. Because cities are not neutral containers, they are engines that can either widen or narrow life chances. Environmental ethics also becomes inseparable from these technologies. Because AI robotics can reduce waste through precision and lightweight design, can enable repair over replacement, and can cut emissions by localizing fabrication. Yet it can also increase consumption by making it too easy to build, rebuild, customize, and discard, and by encouraging novelty for its own sake. And since computing itself consumes energy, the net climate impact depends on choices that are rarely visible in glossy demonstrations, like material sourcing, transport, cement content, machine utilization rates, and the carbon intensity of electricity. A responsible path treats life cycle assessment as a design constraint and treats circularity, reuse, modularity, disassembly, and material recovery as part of the generative brief. While recognizing that efficiency gains can be swallowed by rebound effects if demand grows faster than savings. So the ethics of better building cannot be separated from the politics of how much building we choose to do and for whom. All of these threads lead toward the ultimate question, which is not whether we can sculpt reality with unprecedented power, but what kind of reality we are authorizing through the defaults we set. Because defaults are how systems express values when no one is watching closely. And in complex socio-technical systems, someone is always not watching. If the defaults reward speed over verification, then corners will be cut by algorithm and by manager alike. If the defaults reward proprietary lock-in, then communities will be trapped in maintenance ecosystems they cannot govern. If the defaults treat data as an asset to monetize, then the built environment will quietly become a data extraction surface. And if the defaults treat labor as a cost to minimize rather than a capability to sustain, then the physical world may become more efficient while the social world becomes more brittle. But if the defaults reward safety margins, repairability, and transparency, if they embed human oversight where it matters and automate only what can be audited, if they enforce privacy by design and security by design, if they make training and mobility part of the deployment plan, and if they define success not only as a completed structure, but as decades of healthy, equitable service, then intelligent crafters can become a way to rebuild trust between people and the systems they depend on, a trust that comes not from believing machines are benevolent, but from seeing that institutions have made them accountable. The calmest, most durable future is the one where autonomy is treated as a public capability that must be governed, where buildings that adapt do so in ways that preserve dignity and consent, and where the power to shape form is matched by the patience to shape outcomes. Because the world we sculpt with these tools will not only reflect our intelligence, it will reflect our care. It helps at the end of this long arc to picture not a distant skyline but an ordinary morning in a city that has slowly absorbed advanced AI robotics into its bones, where the changes are felt less as spectacle than as a steadier pulse of upkeep and adaptation, and where the most important inventions are the ones that keep receding into the background because they work without demanding attention. The street is still a street with its familiar noises and routines, yet beneath it a mesh of instrumentation listens for the soft signatures of trouble. Subtle shifts in vibration that suggest fatigue, tiny changes in moisture that foreshadow corrosion, temperature patterns that indicate insulation gaps. And this listening is not an all-seeing gaze, but a deliberately limited set of measurements chosen for public safety. And when anomalies appear, they do not immediately trigger dramatic action, but a cautious escalation. First, a targeted scan by a small inspection robot that moves like a careful animal through service corridors, then a human review of the data trail that the robot leaves behind, then a repair that is as local as possible. If you made it to the finish, I really appreciate you. If you want more slow, soothing science, liking the video and subscribing keeps the next one easy to find. Performed at night by a fabrication tool that arrives, seals, reinforces, and departs, leaving the surface nearly as it found it, so that the city's visible life can remain calm. In such a place, the idea of building as a single event has quietly faded, replaced by building as a relationship, a commitment to keep structures aligned with reality as reality changes. And that alignment becomes especially valuable in a warming climate where historical assumptions about wind, heat, and rainfall are losing their reliability, because infrastructure that can be monitored continuously and adjusted incrementally is infrastructure that can respond without waiting for catastrophe to justify investment. And that is one of the sober reasons these technologies matter beyond their novelty, that they can turn climate adaptation from a series of emergency retrofits into a more continuous practice of resilience, provided we choose to fund and govern them as public goods rather than private conveniences. In this imagined city, design is also different, not because human imagination has been replaced, but because it has been given a broader instrument, a way to explore the design space with more patience than any individual could sustain, and then to bring that exploration into the world through fabrication systems that can honor complexity without turning it into waste. The most careful architects and engineers learn to write constraints like vows, declaring what must never be compromised. Egress, accessibility, daylight minima, ventilation thresholds, structural redundancy, repairability, low toxicity materials, and then allowing algorithms to propose forms within those vows. And the best proposals are often not the most exotic, but the most quietly efficient, shapes that reduce material without reducing safety, details that prevent water traps, assemblies that invite disassembly, and component families that can be replaced without tearing apart the whole. What emerges is not a city of endlessly changing, restless objects, but a city whose changes are constrained, legible, and accountable, because adaptability without discipline becomes churn, and churn is simply another name for embodied carbon, disrupted communities, and short-lived promises. This is also a city where human work has shifted rather than vanished, yet the shift has required deliberate care, because robots that can lift, place, cut, and print inevitably change the labor market, and whether that change becomes a widening wound or a manageable transition depends on policies that treat training as seriously as procurement, and on contracts that require apprenticeship pathways, safety certification, and local capacity building, so that communities are not left with automated infrastructure they cannot maintain or audit. In the calm version of the future, the most valued human skills are not only coding and operations, but the integrated judgment that construction has always demanded. The ability to recognize when a site is lying to you, when a measurement is plausible but incomplete, when a simulation's assumptions no longer fit, and when a schedule pressure is about to become a safety compromise. And those skills remain human not because humans are mystical, but because accountability must land somewhere, with names, licenses, and consequences. As autonomy increases, the city's governance becomes more explicit about what is permitted, and this is where the deepest sculpting happens, because the true shape of a technological era is defined less by its capabilities than by its defaults. A robot that can adjust a toolpath in response to a scan may be allowed to do so within certified bounds, while a robot that could decide to reroute pedestrian flow might be forbidden from making that change without public process. And a system that could personalize indoor climates might be required to do so with on-device processing and strict data deletion. Because comfort is not worth converting buildings into quiet surveillance machines. In other words, the city learns to separate sensing for structural truth from sensing for human profiling, and it writes that separation into enforceable rules, audits, and technical architectures, because the temptation to repurpose data is one of the most persistent temptations of complex systems. Security, too, becomes part of physical design, since cyber compromise can become physical harm, and so critical robotic maintenance systems are built with redundancy, with verified updates, with segmented networks, with fallbacks that fail safe, and with incident drills that treat an attack not as an unlikely aberration but as a predictable stressor. The way engineers already treat storms and earthquakes, and when failures occur they are investigated with the same seriousness as structural defects, because in an automated city, software is a load-bearing element. Over time, this mix of measured autonomy and measured governance produces something that can reasonably be called living infrastructure, not because it is conscious, but because it participates in a cycle of sensing and response that resembles a kind of civic metabolism, taking in information, distributing effort, repairing damage, and keeping itself within safe ranges as conditions drift. And if there is any single moral hinge in this story, it is whether we treat that metabolism as a shared capacity that protects everyone, or as a premium service that concentrates resilience in wealthy districts while leaving others brittle. The difference will not be decided by a robot or by an algorithm, but by procurement rules, building codes, union agreements, insurance models, public transparency. And the quiet decisions of engineers who choose what to measure, what to optimize, and what to refuse. In the end, sculpting reality turns out to be less about commanding matter and more about agreeing collectively on what we will continuously maintain, what we will continuously verify, and what we will never trade away for speed. Because advanced AI robotics can make the built world more responsive, more efficient, and more repairable, but it cannot tell us what a good city owes its people, and it cannot replace the slow, essential work of setting boundaries that keep power answerable to public life. And when those boundaries are clear, the machines can return to their proper role as tools of careful stewardship that help our structures remain stable, breathable, and quietly dependable across the long years.